Okay, well, this gets to be a slightly heavy lecture because I start talking a fair bit of mathematics, and of course it's a crash course. I jump over stuff very rapidly, so when I come back I'll be giving much more detail than I'm giving now, but I'll try to provide some background on how you model phenomena like the financial instability hypothesis that I explained in the last lecture. And the first thing I haven't put much data into the talk so far, which is just again circumstantial, so I thought after talking a bit about Minsky's thesis yesterday, I might show you some data on just how important the change in debt is economically before I start explaining why, and then take the steps necessary to build a mathematical model of Minsky's hypothesis. And is anybody here a fan of the band Supertramp? Okay, yeah. Ever Crisis? What Crisis? Okay. One of my favourite ever albums and album covers, but that's the classic. What crisis? Well, here's looking at the ratio of private debt to GDP in America since the Second World War. Now, I'm continually being told by conventional economists, and particularly in whatever debates I end up having with Paul Krugman, that the level of private debt doesn't matter. You know, one person's asset is another person's liability, so the level of debt doesn't matter. It's only if it gets high enough that it provokes people for some reason to be worried about whether the patient people can be paid back by the impatient people who've borrowed money, but otherwise it doesn't really matter. And the same in Bernanke, and the whole neoclassical trend was to say that this is just not an important economic variable. So just to show how unimportant it is, this is looking at the annual change in debt divided by GDP since 1945. And I think you can see first two things about that. There's an increasing trend. So over time the change in private debt has become larger and larger compared to the level of GDP. And slightly increase in volatility, you might notice. And if you time some of those periods where there's a dramatic decline in the rate of growth of debt, you'll find it sort of coincides with recessions, including the crisis we've just been through. This dotted line, by the way, here is where the rate of change of debt is below zero. Okay? And you notice the entire Second World War period, except until the crisis began, the change in debt was, even though it was very volatile, didn't turn negative until this crisis. Okay? So, what crisis? This is the long-term view. Now, looking back, we've been working with a group called the Governors Woods Foundation in Philadelphia before I came here, and the person who established that, a guy called Richard Vague, was the person who introduced credit cards into America successfully, two major companies, and he's now become a philanthropist, and one of the things he's focusing upon is the role of private debt. So with his help I helped him to go backwards through census data and try to assemble a long runtime series on American private debt. And one of the problems is that because economists don't regard it as important, statisticians haven't systematically recorded it. So it took a lot of work to try to imply what these data series were over time, to get points where there were major differences. The census data from 1916 to 1970 overlapped with the flow of funds data from 1945 to 1970, but differed by a huge factor, so I had to bring down the census data just to make the two consistent, stuff like that. And then I'd use data from bank loans loans by banks as opposed to debts recorded by households and businesses to go right back to 1834. Having done all that, this is the long-term pattern for private debt to GDP in America. So looking at where we are now, the level of debt that the American economy is in now is higher than it's ever been in its recorded history. And the only other time it got particularly high happened to coincide with the Great Depression. Okay? So again, crisis, what crisis? Now, the mainstream theorists focus upon government debt. That's what causes all the paralysis in the American Congress, and it's the obsession of conventional economists. The blue line is public debt. And there's only two occasions where public debt has exceeded private debt. I don't know my American history all that well, but I think that was the Civil War, wasn't it? Okay? And that's the Second World War. So throughout, it's been private debt that's been bigger. And public debt has only risen after some sort of economic or social crisis. The Civil War itself. Notice, by the way, a decline in private debt leading up to the Civil War, a decline in private debt leading up to the Second World War. Okay? And, you know, we've got massively rising debt now. No World War, thank God. There's no way we could survive one this time round. But the pattern throughout is the dominance of private debt. I'm regarded as being on the periphery of modern monetary theory, not all, but you know, I certainly agree with a lot of the arguments made, and certainly I'm trying to build a monetary theory of economics, which puts me in that camp distinctly from the neoclassicals who have a non-monetary theory of capitalism. So they argue that public debt doesn't matter. Now, I'm going to say, well, yes and no. You agree, public debt is not the problem. But when you add the two together, you do see a worrying trend about the extent to which the finance sector and level of debt dominates the economy. So in total, the level of total debt has risen as well over time. There's something empirical we have to investigate about that sort of behaviour. Okay. Though I can argue that private debt's the most important part, this trend over an enormous length of time for rising total debt is something we have to consider as well. And you'll find if you look at the work of Michael Hudson and people like David Graeber and Felix Martin looking back at the history of debt, you find that ancient societies used to have a rule of abolishing debt every 50 or so years, or every change of ruler. Okay, so maybe they knew more about the worries of debt than we did. Because crisis, what crisis? Well, one thing you might remember, I showed you a quote from Bernanke at one point, where he said that absent implausibly large changes in differences in marginal propensities to consume, pure redistributions should have no effect. Therefore, ignore Fisher's debt deflation hypothesis. So that's saying there should be no macroeconomic impact between change in debt and, there should be no macroeconomic impact of the level or the change in debt except during a liquidity crunch, which is the one time that conventional new Keynesian economists will accept that there can be some problem from debt. So this shouldn't happen. This is the correlation of change in debt to unemployment for the last 20 years, 25 years. Okay. What Bernanke calls the financial accelerator, which is a non-quantitative thing, it's a qualitative argument, effectively, or a price argument rather than quantity argument, that would argue some sort of correlation, but not minus 0.9 over 25 years. And a similar thing for the asset markets. This is now looking at the acceleration of mortgage debt and change in house prices over the last 6 decades. Correlation of 0.72. That shouldn't be there, okay, according to conventional theory. So that's why this is something significant that's being ignored by the conventional approach to economics, which is why we have to bring Minsky's analysis into the fold of the general way that economists think about the economy, which involves a model. Okay? It's very, very hard to win an argument in economics without a model. Okay? You get dismissed over time. So I had to build, having read Minsky's verbal hypothesis when I did my PhD, and really finding it very convincing, I found, I showed you the model that Minsky tried to build his model of financial instability on last week, and it was just the wrong foundation. Now, there's plenty of cyclical models in economics. I chose Goodwin's model for the reasons that I explained in the first lecture when I spoke about Marx. One is that if you simply put together the argument that output requires factories, factories need workers, workers get wages, and you feed back to saying where investment comes from, you end up with Goodwin's model. It's a very, very simple, fundamentally structural model of the economy. And it also, the assumption it makes about workers responding to the level of employment is the same argument that Marx uses in that very first dialectic he puts on top of the explanation of where surplus comes from, which is the argument about the value of labour being the minimum wage. There's something that means it will exceed the minimum wage, some sort of struggle argument going on. Now, if you look at Marx, the way he explains cycles and income distribution, I'm going to give you an English translation as well. You've seen it a couple of times. I want to say, just more obviously, in more modern language, what was Marx actually saying. So he said, accumulation slackens in consequence of the rise of the price of labour because the stimulus of gain is blunted. Well, what he meant was that profits fall because of rising wages. Yeah, he's got a two-class model there, so the only outcome of wages go up, trade profits go down. The rate of accumulation lessens, investment falls, less investment taking place. With this lessening, the primary cause of lessening vanishes, the disproportion between capital and exploitable labour power. Employment and wages fall because of slow growth. Okay? The price of labour falls again to a level corresponding with the needs of the self-expansion of capital. Falling wages restore profitability. And investment starts all over again. So that's the vision that Marx had. And in fact, one of the intriguing little sidelines of the history of economic thought is Marx wrote Capital in 1867. That was the publication date of the volume 1 of Capital, but he wrote volumes 2 and 3 as they were later published before he wrote volume 1, and also Theories of Surplus Value. So all the stuff that came out after 1867 was edited by Engels. And while that was all going on, while Marx was still alive, he was trying to learn calculus. And there's actually his mathematical manuscripts are being published now. And I would argue that the major reason he was trying to do it, he was trying to work out how to put that model into mathematical form. He never quite worked it out. But if he'd done it, he would have preceded the discovery of nonlinearity in economics, in mathematics, by about 50 years. So how did Goodwin actually translate that mathematically? Well, he started by saying level of output determines employment. And if I put that within the Minsky framework, they have Y divided by LP for labour productivity becomes L. But then employment determines the employment rate. We simply have to divide L by the population level to get the employment rate, which I'm using the symbol lambda for. And then lambda determines the rate of change of wages, and a very simple function here. I partly use this to satirise neoclassicals because of Friedman's argument about what he called the non-accelerating inflation rate of unemployment, equilibrium concept. Well, I just simply have that here and say, let's imagine there's some equilibrium level of unemployment for which wages don't change. Then my Phillips curve function is saying the actual level minus the equilibrium level multiplied by how much the workers respond to each percentage difference between the unemployment rate and this equilibrium rate is the rate of change of wages, wage function here. And if I multiply that by the current wage and integrate it, I get the wage, the straight differential equation. I'll show that logic a bit more carefully later. Then wages times, the wage level times the number of workers is the wage bill. And then you subtract that from output, you have profit. Okay. And then if all profits are invested, which is the simple assumption that Goodwin made in that model, then profit becomes investment, which is the rate of change of capital stock, and capital stock determines output. So you tie it all together. Now, I've normally shown you a cyclical model in Minsky, but one reason we designed it to have the variables there is you don't have to use wires to link everything together. If you want to use actual variable names, you can do that instead. So that closes the overall causal loop, and I'm showing it here as one long strip. So I start off with output, and I get to output at the end. So it's a causal loop between the two. So you have, just to go through again, output divided by labour productivity gives you the number of workers you hire, divide by population gives the employment rate, subtract that from equilibrium rate gives you the gap, multiplied by the linear function for how much workers respond to that, you have the wage change function, multiply that by wages, integrate it, you get the wage level, multiply by labour, you get the wage bill, subtract from output, you get profit, assume it's all invested, that's the rate of change of capital stock, divide by the accelerator relationship, you get output. Okay? And when you simulate it, you get cycles. So what I'm going to be explaining for a while now is where those cycles come from in a mathematical sense. I've embedded this that particular model in the PowerPoint, by the way, so if you just simply click on it and you've got Minsky loaded on your computer, then this will come up and you can run the simulation live, and you can also save it onto your own computer, separate to the PowerPoint presentation. So I've done it for all the models I've put together in this lecture series. So, why is it cyclical? Why doesn't it converge to equilibrium? There's this belief that economists have everything has to get to equilibrium ultimately. And a lot of post-Keynesians have a similar argument. Just to give you an anecdote, when I first began doing my PhD, my master's degree, I'd already done a fair amount of mathematics before that. And I was discussing with some of my post-Keynesian colleagues about dynamics. They said, yes, the traverse. And I said, what do you mean by the traverse? And they said, oh, that's the dynamic process of going from one equilibrium to another. And I said, why do you have to start in equilibrium and end there? But there was just this belief that that's what dynamic systems do. And what dynamics tells you is the movement from one equilibrium to another. That is very ignorant of dynamic systems and mathematics in general. So, but I need to give you some maths to explain why. And I can't go into the full details given it's only 5 lectures. But if you take that model, which so far if you take a look at it, I've shown it to you in terms of absolute levels, output, wages, etc., etc. But if you analyse the model and say, can I reduce it to a couple of fundamental determining variables, it comes down to 2 ratios, the employment rate, okay, and the worker's share of output. And when you put it in those terms, that's a set of what are called reduced form equations you get. The rate of change of employment, then if you actually just bring across the lambda here and say 1 over lambda d lambda dt, that's the percentage rate of change of the employment rate, is equal to 1 minus the wages share of output divided by the accelerator minus labour productivity and population growth. And this one says the rate of change of wages is the wage function minus labour productivity. And in fact, you can actually make quite nice verbal statements about that, saying if the rate of this is actually the rate of economic growth. So if the rate of economic growth exceeds labour productivity and population growth, then the employment rate will rise. That's a verbally sensible statement about the capitalist system, about an economy, period. And this is saying if workers' wage demands exceed the rate of productivity, they'll get more of output. That is also a sensible verbal statement. So you can often get quite sensible verbal propositions out of mathematical statements like that. But anyway, yeah.
I'm just wondering whether like with some simple expression of W, this could be resolved analytically. So we don't need the program to say that it's cyclical.
I think you're probably leading. It's a leading question from you because you know enough mathematics to make it into a leading question. Yeah. Yes, you can solve this analytically, but it's the last level of complexity which you can get an analytic solution because it's 2-dimensional. Once you go to 3 dimensions, there is no mathematical solution. Were you leading that way?
Yeah, I mean at least for this one.
Oh, for this one you can, yeah. What you can reduce it to is a pair of exponential equations where the rate of change of the lambda is a function of e raised to the power of omega, and then vice versa. So you do get an analytic solution for it. And that comes down to a whole range of stories about what are called conservative versus dissipative systems, and a lot of stuff that if I do come back here and teach on a permanent basis, I'll go into more detail over it. It is the very last level you can get an analytic solution for. This is another important point about the naivety of economists. Again, a very good friend of mine and a great conventional economist and a bloody good tennis player, once had a seminar where another friend of mine was saying that he believed chaos theory would, change economics. And the first guy said, I'm sure I can prove a theorem that chaos theory makes no difference to international trade theory, which he then duly went off and did. But he used what are called conservative systems rather than dissipative. I didn't even bother commenting on the paper. And the belief you can prove a theorem is an economic belief that everything can be proven in economics. But mathematicians know that once you get past the 2-dimensional system in dynamic senses, you cannot prove the outcome. There is no analytic solution. So you have to go to simulation and you have to go to numerical investigation after that. So back to this little one here. Whether this gets attracted back to its equilibrium, and there is an equilibrium there. Okay? If you look at this, to make equilibrium, this expression, 1 minus omega over v, has to equal that expression. That'll give you 0 rate of change in employment. So your equilibrium there is going to be, I think it's omega equals v times 1 minus alpha minus beta. Okay? And this one, your equilibrium, is if you've got to do a transformation of the function here, but the inverse function of this has got to be equal to the rate of productivity growth. So you can get, those are the equilibria there. Now, will it return to them? Well, that depends on whether the dynamics are pushing you away from equilibrium or pulling you back towards it. And that's involved a thing called an eigenvalue. And has anybody heard of an eigenvalue? Put your hand up if you have. Okay, a lot of that's great. That's good. That's good training. I'm glad to hear it. Often I get very, very small number of hands going up when I talk in Western universities. But that is a way of resolving the pushing and pulling of a multidimensional force like this, where I've got two variables, employment and wages share, into whether it's pushing you away from the equilibrium, which in a continuous time system means that what's called eigenvalue is greater than zero, or pulling you back towards it, which means it's less than zero. Okay? So, and there are normally as many eigenvalues as there are dimensions to a system. So the one that matters is what they call the dominant, which is the biggest. Now, in this particular model, that dominant eigenvalue is neutral. What's called the real section of that is zero. The complex system, who's heard of complex numbers? Another test. Who hasn't heard of complex numbers? Okay. Again, that's why you have to learn complex numbers to handle cyclical logic. And again, most economists don't learn that. But it's neutral. Now, it'd take a fair bit of mathematics to get into the logic here, because I've got to do transformations of a function and so on. So I'm using an analogy here instead to the predator-prey model. And as it happens, Richard Goodwin learned his mathematics from the French mathematician who was one of the leading exponents of predator-prey models. But predator-prey involves things like fish, who are if there's abundant seagrass and no sharks, the population would grow indefinitely. So as an equation, you can simply say 1 over f df dt equals a. And it's exponential population growth. And you might have sharks as well, and if there are no fish around, they're going to starve to death. They'll eat each other before they starve, but they'll starve to death over time. So as an equation, you can say 1 over s dt is minus another constant, say c. Now, if you put those together as an integral equation, what you have to do is first of all you start from that expression, which is that is simply a statement of a percentage rate of change. Then you multiply across by f, so you have a differential equation now, df dt equals a times f, and then you integrate that, and you get the equation finally, f is equal to the integral of a times f plus a constant, which is the initial number of fish. Okay? And you do that in Minsky, that's what the equation becomes. A multiplied by f, integrated is f. And you put an initial value for the number of fish inside the definition of f. So to build the model, did a little movie. Now off we go. So down comes f, or either an integral block. I define that as f, give it an initial value of 100. Then I want a constant, which I'm just going to call a and give it a value of 1. So that's saying population doubles every year, 100% rate of growth. Go across, right-click and choose copy the variable, bring that across. Now watch this magic here. In the latest version of the program, I can simply hit the multiplier key at that point and get a multiply block. That's not yet in the version you've got, but it's coming up in the next version. Wire that up, and that's the equation. And then let's put a graph there. I think I'll bring out sharks next. What I'm doing? No sharks. Okay, here we go. Same story, right-click, S, give the value of 10. Constant of C. I'm going to make that, I think, minus point. I'll make it 0.1. But of course, I've got to make it minus 0.1, so I need a minus key at that point. So bring down the S first of all. Now press the minus key. And then to invert, to get minus C, what I do is I simply put the C itself through the bottom of the minus block and don't wire anything to the plus. So that then lets me wire up minus C, multiplied by S, integrated as S. That's the start of the model. You always spend your time retidying these things up, I'm afraid. It's one time-wasting thing about graphical user interfaces, but nonetheless we have to do it. Second graph down here. y those up. I'm changing the run to kind of make that 0.01 to get a smoother plot. And you get exponential growth of one population, exponential decay of the other. So that's the basic idea then. So, to link them together, the simplest argument you can make is that the sharks are being around linearly reduces the growth rate of fish. That's the simplest possible assumption you can make. It'll be more complex in the real world. In fact, this model was first invented after I think it was actually during the First World War, by an Italian mathematician and an Italian biologist, because the biologist was recording the number of fish being caught in a seaport, a statistical study. Why is it so hard to say the word statistics? A statistical study. I need another coffee. And what he found was an increase in the number of sharks turning up. And he asked a mathematician to say, what the hell's going on here? And the theory that the mathematician put together was, first of all, this predator-prey relationship between the number of sharks and the number of fish. But then he said there's a third predator, or second predator, which are the fishermen. And because they were off fighting the war, there were less of them. And because of less of them, there ended up being more sharks compared to fish. So that was the first time this model was done. The one I'd like to use sharks and fish for it. So you can say sharks linearly reduce the rate of growth of fish, whereas fish linearly increase the growth rate of sharks. For putting that together in equations, I can now say 1 over ft is a minus b, which is constant, times how many sharks there are. And the same for sharks in reverse, plus d times f. In integral form, then it becomes that, which I then make f is equal to the integral of a times f minus b multiplied by s. Now this is extremely important, multiplied by f as well. I've got the two variables multiplied together. So it's nonlinear. It's like, I call it that a semi-quadratic. Okay? Two variables are not f times f, which is a pure quadratic, but f times s, which is one variable times another. So it's a natural nonlinearity. I'm not imposing an assumption of nonlinear behaviour by the sharks. It is simply that the mathematics, the structure of the model means you've got the number of fish multiplied by the number of sharks. And the same for the sharks equation. So you put that together in Minsky, and this is what you get. I stuffed up the recording. I didn't actually save the first model. I had to start the whole damn thing again. So I might save time and just jump past that and bring it up. I think here we go. Hit the key too quickly. Let's go. Pardon me. That's the model now put together, but very messy, as you can see. If I simulate it in equilibrium, that's what I get. I'll just stop that. If I can stop that for a second, let's see. I can't. That's the equilibrium result. No change in fish, no change in sharks. The reason was the numbers given the numbers I chose for the parameters and the numbers of initial fish and sharks I chose, I'd actually hit the equilibrium. But if you are away from the equilibrium, then you get the same sort of cyclical behaviour I showed you for the Goodwin model. If I do an XY plot, which I'm writing up here at the moment, then you get that same closed loop. Okay? No matter how extreme the numbers, I chose quite extreme numbers for the initial conditions given the parameters I've got there. So just to bring, I think I tidied it up in this particular one. Let's take a look and see. Yeah, slightly tidier. So you simulate it, and there you get your cycles. And if I change that equilibrium, if I change the value there, I had, I've actually got 10 there. What have I changed elsewhere? I must have changed the, hang on a sec, let's see, try it again. I've changed the run-up before I did that. I must have worked another number in for C and D. I'll check that later. Okay. Now let's work out the equilibrium of the system. This is an intriguing little outcome. Equilibrium is where the rate of change of each of those differential equations is 0. So I've got to have And I put F underscore E here to make it obvious I'm talking about an equilibrium value. Okay? So in equilibrium, the rate of change of the system is 0. So A times the equilibrium number of fish minus B times the equilibrium number of sharks times the equilibrium number of fish is equal to 0. If you solve that equation, what you get is the solution for how many sharks there'll be in equilibrium out of the fish equation. And the parameters that matter for the sharks are the parameters you use for the fish, A over B. And the same thing for the sharks equation. You do that and you solve for the equilibrium number of fish. So that's your solution overall. Now, as you saw, it neither converges nor diverges. It continues cycling around. And that can happen for one and only one type of linear model, one particular condition, but it's a common potential phenomenon for a nonlinear model. And nonlinearity is extremely important because if you look at a linear model, you can get cycles. So an equation like that, which is a second order linear differential equation, can give you cycles. But its cycles have a particular characteristic, and nonlinear ones don't have that characteristic. That's extremely important. Now, who's done differential equations here? A few. Okay. Again, quite a good number. I'm pleased. Well, you know the basic idea. The way you solve this equation is you guess an answer. I think that's called the ansatz approach. And the guess you make is that the solution is the exponential raised to some power times time. And that's a guess because of the nature of the differential equation. If you differentiate e to the x, you get e to the x. Okay? That's the reason for that particular trick. And then you work out what r has to be to solve the equation by doing substitution. So there's the overall equation, and I've now guessed that the answer is e to the r times t. So the second differential is going to be a multiplied by r squared times e to the rt. The second is b multiplied by r, and the third is just c by e to the rt. What you can then do is group your terms, and what you get is all e multiplied by the rt multiplied by a quadratic in r. So the solution, what the value of r is going to be a quadratic because e to the raised to any power is greater than 0. So we know the first bit can't be 0, so somehow the value of the second bit has to be equivalent to 0. Therefore, that r has to have the value of the root of that particular quadratic equation. And that quadratic equation, we all know the formula for a quadratic. You can't escape that at school. So we know the value is going to be r is going to be minus b over 2 times a plus or minus b squared minus 4ac all over 2a. Now the solution is therefore, when you feed it back in again, is going to be yt is going to be e raised to the power of minus b over 2a times t multiplied by e raised to the power of plus or minus the discriminant multiplied by t. Now this bit causes cycles. If that happens to be a complex number, the square root of a negative number, then you'll get cycles. This bit tells you whether you're going to converge or not. It's the magnitude of those cycles. And you can see you completely separate the two. Magnitude and cycles are completely independent in a linear model. So whether it converges just depends upon the value of minus b over 2a. And so if minus b over 2a is less than 0, a negative number, then the system will converge to equilibrium from wherever you might start. This could be a model of an asteroid in the solar system, and if minus b over 2a was negative and the asteroid was 100 million miles away, it had hit the sun. If it was a billion miles away, it had hit the sun. Equally, if minus b over 2a is greater than 0 and the asteroid was right next to the sun, it would leave the solar system. Okay? It just, no matter how close you are to equilibrium, no matter how far you're away, this one number determines whether you converge or diverge for a linear system. But in a nonlinear model, you can't do that. The magnitude and the cycles are entwined. So a model can converge a long way from equilibrium, so the asteroid could be way out, past Jupiter, and come back and bounce around the sun and get pushed back out again. Or it could be right next to the sun and get blasted out and then come back again. So a nonlinear system, you can't separate the magnitude from the cyclicality. And there's a bit of mathematics involving it, which I'm not going to cover here again because of time. But that's the fundamental difference between a linear system and a nonlinear one. In a linear one, if it's unstable everywhere. If it's stable, it's stable everywhere. A nonlinear can be unstable close to the equilibrium, unstable far away, or vice versa. You can't simply decide it by that one number. So if you have a nonlinear system and it's stable in a particular part, then it might be stable elsewhere, or you just can't characterise it in that simple way. So the linear model, there's your opportunities. You know the Chinese hats or the Vietnamese hats? They're like a perfect cone. Imagine having a perfect cone and you turn it upside down and you drop a ball bearing into it. It's going to fall to the bottom, no matter what, no matter where you drop it. Okay? If you put it on a tabletop, it might roll around a bit, but it'll stop somewhere on the tabletop. And if you have the hat upside down, you drop it, it's going to run away. That's the only choices you have for a linear model. For a nonlinear one, both is continuing with the linear. So if it's stable, all your eigenvalues are going to be negative, and you're therefore going to converge to equilibrium. If it's unstable, your eigenvalues are going to be all positive, you're going to diverge away. You can have a mix of the two, and funnily enough, what's called real business cycle theory involves having this particular instability and then arguing that agents are able to guess where the instability is and jump onto it with perfect foresight. Another insane concept. So you can be stable one way, unstable the other. To a mathematician, that's an unstable system. You won't reach equilibrium. To a neoclassical economist, the rational agent works out where the disequilibrium is and jumps on top of it and cycles up and down. I can't believe some of the stuff they get into. With the nonlinear one, I think a sombrero is a better model. Yeah? If the sombrero is that way round, then you'll fall to equilibrium. If you're close enough, you'll move further away. If you're not, you'll come to, if you drop the ball bearing, it really depends on where you drop it as where it's going to end up. And if I turn the sombrero upside down, then the equilibrium is unstable no matter how close you are to it. So to understand a system like that, you have to simulate it once you get beyond 2 dimensions. And then you analyse the property of that using stability analysis and perturbation theory and a whole range of other techniques. So that's a long-winded explanation without enough detail to show you what's going on. But the Goodwin model and the predator-prey end up having, when you do the nonlinear analysis of them, the real parts, their eigenvalues are 0, so neither pushed away nor pulled back towards, whereas the other part is, the complex part gives you cycles. So, back to the Goodwin model and adding Minsky. What I might do is take a break at that point. Okay, that's preparatory. For the rest of the lecture, it's how to add in depth deflation, coffee break time.